So I will be presenting our work titled toward LLM Agents for Model-Based Engineering, a case in transformation selection. So this is a joint work with Théo Le Calvar, Hugo Bruneliere, and Massimo Tisi at IMT Atlantique in the NAOMO team. So our motivation is to see how LLM-based agents can enhance the model-based engineering tasks. So in this talk, I will follow a structured path. I will start with the introduction, then I will move on to the background and motivation. I will then present the approach, which is an LLM-based transformation agent. I will discuss after that the process we did for the dataset generation to evaluate this agent. And after that, I will also present the experimental evaluation setup. And finally, I will finish by a conclusion and the future work direction. So mainly our motivation came from two directions. The first one, we know that model-based engineering relies heavily on tools, spanning from transformation tools, DSL tools, MF views tools, to model validation and verification tools. And here's the problem. Those tools are difficult to manipulate and require domain-specific expertise. And in some cases, the user might not be aware of the existence of some of them. And on the other hand, we have the rise of LLMs that uses LLM as an interface with users and understand natural language instructions and also orchestrate tools. And to make this orchestration consistent, there is the model context protocol that plays a key role in standardizing the way we expose tools to the LLMs. So the question here, can we build LLM-based agents that enhance the transformation selection? And before answering this question, I'd like to point that in industrial settings, security and control are very essential. And it is the case in the European project Matisse that works on maintaining and validating the industrial system using digital twins, where use case providers need that their system remain protected, while of course having an integration with the digital solutions. So we know that cloud-hosted LLMs can raise concerns about data privacy and control, essentially when we are dealing with the sensitive data integration. So here, locally, LLMs such as Olama can be a preferred choice in this case. So to illustrate this, we take this transformation, this ATL transformation named UML activity diagram to AMS project, to Microsoft project. So this is an ATL transformation, and basically ATL is a transformation language used in model-driven engineering, and it shows us how to map elements from a source model into elements into a target model, and of course the source and the target model should be conforming to their respective meta models. In this example, we have an activity diagram, and using this ATL transformation, we transform it to a Microsoft project representation. And here, we can imagine this case. A user wants simply to do this transformation and simply ask, can you transform this activity diagram into a Microsoft project? Of course, a traditional tool would fail because it expects the user to give the exact configuration of the transformation, so this transformation can be executed. And this is where the LLM-based agents can bridge this gap, let's say, and can first interpret the natural language instruction, then look for the exact transformation, and then execute it in the background. And to do so, we plug the LLM Copilot agent with the Llama 3.2 model, and we repeated this exact instruction several times. Can you transform this activity diagram? And we give the model into a Microsoft project representation in the table. And we noticed that in 100%, there is no correct tool called and with the correct parameters. And this is at this stage, this is due to the genericity of the MCP transformation server we plugged, because we gave just generic ATL transformation servers that has only some generic tools that didn't give much context to the LLM. So the LLM find it hard to find the transformation that respects to the user request. So this is highlights the need of a more enhanced approach where we give LLM much context about each transformation, so the LLM can know how to select the correct transformation with the correct parameters. And this is what we do. So the first step was to give the LLM much richer context. So for each transformation, we build two tools, two dedicated tools for each transformation. So we take a list of transformations, then we generate descriptions for each transformation, and we generate after that two tools for the transformation selected. And this is iterated over the whole list of transformations. So for example, if we take the UML activity diagram to MS project transformation, we should have two tools. A tool that get the details and display the configuration details of the transformation, and a tool to apply this transformation to a specific model. Then when we do this process for all the transformation, we have this prompt template that contains the prompt engineering techniques such as model, such as role-based prompting, and a few shots. We give some example to guide the LM to have a better accuracy at the end. And we inject all the description of the tool so the LM can choose between the tools listed in those tools in this variable that contains the tools descriptions. And after that, we can build the LM using our model llama 3.2, the list of the tools, and of course the prompt that we built earlier. But we noticed quickly an issue. So as the number of the transformation grows, the transformation agents start hallucinating because the LM hits each context window. And we see this when we used more than 12 transformations. So basically, the agents start hallucinating, giving inconsistent results. For example, there is no tool called for some instructions, or the LM start calling the tools very randomly. So here in this stage, we give the LLM much context, but we need a more scalable and stable architecture of the agent. So this is the second step of the solution, where we scored the tools based on the user instruction. So we have the user instruction first, and for each we iterate over each 6 tools. We give the LLM the 6 tools per 6 tools, and then we ask the LLM to score the tools, the relevance of the tools based on the user instruction, and using of course a scoring prompt when we guide the LM to have a to guide the LM to score the tools in respect of the user instruction. So this is a process done iteratively, 6 tools per batch, and then we pass here. The idea is to pass and inject at the final stage just the relevant tools to the LLM, so we don't hit faster the LLM context window. So only the relevant tools respecting to user instructions are passed to the construction of the agent, and we have a version of an agent that addresses the scalability limitations by the tool filtering and the scoring by the LLM. So for example, if we take the same case of the first slides, if we have this kind of instructions, can you transform this activity diagram into a Microsoft project representation in a table? We will have these tools listed with a higher score. The tool that lists the configuration of the transformation, and the tool that applies the transformation to a model, to an input model. So to evaluate this agent, we need resources. So the first thing that we do is that we return to the ATL zone that contains all the ATL transformation. But we quickly noticed 2 problems. First one, the resources were scattered. So the meta models and the models and the transformations were not in the same folders following the same pattern. And sometimes we had missing files, or the transformation were not directly executable. So we reorganized this manually into a unified repository where we had where we organize 55 fully operational transformations across diverse domain. And then we build REST API endpoints and we implemented MCP. So at this stage, we had a server that can be plugged with any LLM that uses MCP, and that's it. So we have a directly usable by LLM agents for the selection and execution to this server. But to really evaluate this agent, we needed a pair of instruction of a real-world instruction coupled with the correct API calls. So we need those natural language instructions. So we had this process where we started with seeds to guide the generation of the LLM, and we categorize these seeds into levels, and each level have some placeholders that we know in advance. And we use LLM at this stage to paraphrase those seeds. So we have a reformulation of these seeds used by, we use the Llama 3.2 to do this task. So at this stage, we have 100 single tasks templates and 100 multitasks templates. Then we check those templates if they are conform. So we manually verified those templates, and we verified if each template in each task level contains the correct placeholders. And so the result is 200 verified, human verified templates. And after that, we injected the values from the server that we built and we talked about earlier into those templates to have the final ATL dataset that contains 1,200 instructions. And I would like to point that this dataset generation process can be applied to any model-based engineering tasks. So here the result is a human-like instructions coupled with the ground truth API call. In the evaluation settings, we have now this complete dataset, and we iterate over each element. Instruction, we pass it to the LLM that we want to evaluate, and then the LLM give us the tool that the agent called, and we have this list of tools called by the agent and the parameters. So we compare the tool called and the parameters called by the agent with the ground truth element, and we do a match in values. If the values are the same, we give a score 1, and if the values are not the same, we give a 0. And finally, when we finish this iteration, we calculate an average score that represents the accuracy of the agent over this dataset. We compare our transformation agents that contain the dedicated tools per transformation plus the tool filtering by the LLM scoring. We compare it against 3 other baselines. The first one is the baseline that has no dedicated tools, so just generic tools. And this is the generic ATL server that we used at first when we used it in Copilot agents. The second agent, it has the dedicated tools per transformation, but there is no filtering. All the tools are passed to the agent. There is no filtering. There is no relevance score computed in this version. And the last agent uses dedicated tools per transformation and calculated the relevance using RAG. So we filter the relevant tools using RAG with the tool names and arguments and descriptions. So let's look at the results. We can see that the blue one, this is the no filtering, drops sharply after 12 transformations. So this highlights the fact that the LLM context window is hit. So after that, we start having hallucinations and the correct are inconsistent. The red line is the one that uses just generic tools. There is no much context given to the LLM. And we can see when we increase the accuracy, when we increase the level of the instructions, the accuracy of this agent drops. And we have also the black agent that represents the tool filtering by RAG. It's highly it has a more accuracy than the two because we use relevance. We have relevant tools that are passed to the LLM, and you can see that our transformation agents can maintain a good accuracy even when we increase the level of the instructions, even in the hard settings. For the multi-tool instructions, where we use the multiple tools, the trend is pretty, it's the same. It's similar to the single tool task. But we can see also that our agents maintain a good accuracy against the three other agents, even in the multitask scenario. And they are the more like word scenario when users want to use multiple tools and to interrogate the agent. So to summarize our contributions, the first thing is that we designed and implemented a model transformation agent with tool filtering. We have an ATL MCP server that contains now 55 operational transformations. Also, we released a dataset generation process that can be applied to other model-based engineering tasks. This contains, in our example here, 1,200 instructions. And the result, we had a higher accuracy, especially on non-trivial tasks when you use multiple tools. And the scale is 55 transformation now. And potentially we can have more transformations. So regarding the future work direction, we can think of enriching the tool descriptions of the tools, because now we have a, let's say, simple and intuitive description of the tools. We can enrich that by adding more transformation constraints and rules, and can inject this information to the LLM. And of course, we shouldn't hit the context, the LLM context window limits. We can, of course, extend this ATL MCP server and to maintain more transformations, because now we have only 55 operational transformation. And third, we can also explore the multi-agent collaboration to deal with the more complex tasks that requires, for example, model recommendation and transformation, or automated model view. So thank you all, and I'll be happy to take questions.